properties of matter, we have three topics to discuss. First one is elasticity, second viscosity and surface tension. So today we will discuss about elasticity. And what is elasticity? Let's say when a force is applied to a material and due to that force the material shows a change in length. That change in length can be an increase in length or a decrease in length. After the change in length, when the force is removed, the material comes back to its original position, the original length. So then that material is said to be showing elastic property, and that is called elasticity. Let's take a material like this. When a force F is exerted, it will show an extension of simple E, a change in length of simple E, and this is the original length of the material, and the cross-sectional area, let's take it as capital A. So here the force per unit area, that is F force per unit area divided by A, this is called as stress. And extension per unit length, that is extension E, unit length, that is the original length of the material, simple L, this is called as strain. So the unit of stress is force Newton, therefore Newton per square meter, but strain, since extension and the original length both are measured in meters, the units get cancelled off, therefore strain does not have a unit. For a given material, the ratio between stress and strain, it is a constant. For a given material, the ratio between stress and strain is a constant, and that constant is given a special name. It's called as Young's modulus, depicted by the symbol capital Y. Since strain does not have a unit, Young's modulus have the exact units of stress, therefore the unit of Young's modulus is also newtons per square meter. And now we are going to talk about the Hooke's law of elasticity. This law was first found by the scientist called Robert Hooke. So he says that within the proportional limit of an elastic material, the stress is directly proportional to the strain. In Hooke's law of elasticity, it says that within the proportional limit of an elastic material, the stress is directly proportional to the strain. That is, stress is directly proportional to the strain. Stress is F over A, we discussed this before. Directly proportional to the strain is extension over length. So we make this an equation by inserting the constant we talked before, the Young's modulus. Hence we can write this equation F over A equals, and we insert this equation Y E over L. This is the equation derived using the Hooke's law of elasticity. This is the equation we use in elasticity. In doing sums, we use mainly this equation. Using the above relation also, we can get the same equation, that is, when we subject stress on this side and we take the strain to this side, we get the same equation. It is this. So here F is force applied, A area of cross section, Y the Young's modulus, E extension, or it can be a compression. Extension is an increase in length, compression is a decrease in length, and simple L here is the original length of the material. So this is the stress strain curve for a material under force. On the x-axis we have the strain and y-axis stress. Let's take a string as an example for a material. At this point O, the force exerted on the string is 0, and when the force is increased little by little, the stress strain curve will be going on a straight line up to A. This OA region, during this OA region, the stress is directly proportional to the strain. That is, this OA region, in this OA region, the string obeys the Hooke's law. That is, we can use the Hooke's law equation F over A equals Y E over L to this region only. We discussed the equation before. So the Hooke's law equation can only be used on this string during this region. This is the proportional limit that Hooke's law states in his law. So the point A is proportional limit, and when the force is further increased, it will reach the point B. Point B is called as elastic limit. That is, at the point B, when the force exerted is removed, when it is removed, the string will come back to its original length, the original position along this graph. It will come back here along the graph. That is why it's called as the elastic limit. It shows the elastic property. And when the force is further increased, it comes to the point C. It is called as the yield point. We can see there's a curve during this BC region. There is a curve. This curve is due to the layers of the material. They start slipping over each other. That's why there's a curve. So C is the yield point. And beyond C, when the force is further increased, beyond C during this region, and it will show the extension. And when the force is removed, let's take point C dash as an example. When the force is removed at C dash, the string will not come back to its original position along the graph, but it will move along this dotted line and comes to the point P and will show a permanent extension. It will show a permanent, this is the permanent extension. So beyond the yield point, when the force is removed, it will not come back to its original position along the graph path. It will follow the dotted line and will show a permanent extension. And when the force is further increased even more, it will come to the point D. Point D is the breaking stress. That is the maximum point of the curve, the maximum point. And when force further increase comes to the point E, and that is the breaking point. At that point, the string will break by reducing its area. So this is the stress strain curve for a material under force. Now we have to discuss about the relationship between Spring's constant and Young's modulus. So between the Spring's constant and Young's modulus. So the equation with Young's modulus in it is our Hooke's law equation, that is F over A equals Y E over L. Now you know the terms: force, area of cross section, Y Young's modulus, extension, initial length. And the equation with Spring's constant in it, it is the equation we use in dealing with springs, that is F equals Kx, force exerted, K is the Spring's constant. K is the Spring's constant. and x here is used for the change in length or extension, change in length. So when we subject f in this equation on this side, we get f equals, we take a to the other side, y, a to this side, a divided by initial length L, and we take this extension aside for a while. Just I have to show you something like this. This is the equation when f is subjected on this side, and here f is the force exerted. Here f, it is also the force. E extension, x stands for extension. Therefore, when we align these equations like this, when we take this equation here, we get f equals k x, like this. So you can see here force, force, extension, extension. So this is compatible, this is compatible, hence this k, that is Spring's constant, must be compatible with these terms, hence we can get an relationship between k and Young's modulus, that is k equals y a over L initial length. We can define them here. K is the Spring's constant, y the Young's modulus, a area of cross section, and L is the initial length. So we got an equation for the relationship between Spring's constant and Young's modulus, that is k equals y a over L. This is the relationship between the Spring's constant and Young's modulus. How can we calculate the energy stored in an elastic material? So if we take a elastic string as an example, having an initial length of simple L and area of cross section of capital A, and when this string is subjected to a force F, let's say it shows an extension of simple E. So the initial force exerted on this string is 0. Initially there is no force, it remains in its initial length, no force. But after an extension of E, the force exerted is F. So when we get the median force is the initial plus after an extension of E, and we divide it by 2. This is the median force. Therefore, to get the energy stored in the string after an extension of E, the median force, we have to multiply it by the distance, that is we get half this F, the distance or the extension E. Let's take an extension of E for an example. So this is the relationship of energy stored in a string. So we can get the equation, that is E equals half F E. This is the equation we use in calculating energy stored in a elastic material. This is the energy stored, force exerted, and the extension. So if we have to find the stored energy of the string per unit volume, then we have to divide this energy. We have to divide that energy. This is the energy per unit volume they are asking. So we have to divide it by the volume. So what is the volume of this string? The volume is the area of cross section into length. So we get AL, that is the volume. So we substitute this equation here for V, and we can get E, the energy stored per unit volume, half FE. We have to substitute this here, so you get AL. And when we separate these terms, we can see here this is F over A, E over L. So when we separate these terms, you get half into F over A into E over L. So you can see here this is special. F over A is the stress, E over L is the strain. So we can build up the relationship for energy stored per unit volume, that is half into the stress into the strain. This is the relationship for stored energy per unit volume, and this is the normal equation we use to calculate the energy stored in an elastic material. Now let's talk about the extension or compression taking place due to temperature change. Let's take a rod which is slightly kept in between two fixed supporters. That is, this rod is kept in between these two fixed supporters. It is not fixed, that is, there are no force exerted at the either ends of the rod. There is no force exerted on this rod, and let's say the temperature is increased by theta degrees. The temperature is increased by theta degrees, and now let's take the original length here as simple L, and the temperature is increased by theta degrees. Normally the rod should undergo a change in length, an increase in length due to this temperature change. That is this. This is the extension that should be undergone by this rod due to the temperature change. But since this rod is fixed in between two fixed supporters, these supporters can't move. Hence, the rod will remain its original length. But in a normal situation, since there should be an increase in length, but here now it's not. Therefore, in this instant, a compression. There is a compression. The rod is compressed due to these two fixed supporters. That is, there is a force acting on this rod by these supporters on either ends. Let's take it as F. So now we are going to find the force exerted here. First we will take our original equation, the usual equation, F over A equals Y E over L. Here now we know the terms: force, area of cross section, Young's modulus, extension. In this case we are talking about a compression and the original length. How can we find the compression here? For that, we are going to use an equation from our heat lesson, that is delta L equals L naught alpha theta. This is the equation we are going to use. So here delta L is, in this case we are using this symbol, so that is E. Delta L is the change of length. In this case it's a compression, that is this length, and L naught is the original length. In this case it's the original length of this rod, that is L. Alpha is the coefficient of linear expansion. Alpha is the coefficient of linear expansion of the material, and theta is the temperature change. And we are going to use this equation here and rewrite the equation. F over A. A is the area of cross section of this rod. F over A equals Y. For E we are substituting this we get L alpha theta divided by the original length L, and L to L get cancelled off, and we take this area to this side, we subject F in this side, and we get F equals Y alpha theta A. F equals Y alpha theta, we brought this thing here A. So this is the equation we use in calculating the force exerted on a material in an instant of temperature change. That is, it can be a compression or an extension. So this is the equation we use to calculate this force.
මෙම වීඩියෝව ඔබගේ දැනුමට උපකාරී වුණා නම් ලයික් කරන්න. මේ වගේ තවත් වීඩියෝස් බලන්න අපිව සබ්ස්ක්‍රයිබ් කරලා බෙල් අයිකන් එක ක්ලික් කරන්න. ඔයාලගේ යාළුවන්ටත් දැනගන්න ෂෙයා කරන්න අමතක කරන්න එපා.